Alright guys, we're back at it again. I want to try to make this quick, but if you do have any questions, once again, feel free to just email me. I'll try to get back to you within a school day, probably within 30 minutes of you emailing me, usually even quicker than that if you ask any of your friends. So what we're going to be looking at today is finding the sum of the first n terms of a geometric sequence. We just did that with arithmetic sequences, but this one's a little different. In this case, what's happening whenever we're finding a sum, when we have this term, in our last case, what we had is we had a sub 1 plus r times n minus 1, and that was where we were adding a common difference every single time. Now what's happening is we're multiplying by a common ratio, so it's slightly different. I'm going to go ahead and try to walk you guys through this the best I can. So the sum of the first n terms of a geometric sequence denoted by s sub n, this means your sum of the first n terms, and it's called the partial sum and can be found without having to add up all of your terms. And what we're going to do is just go right on into it. So the basic kind of principle is we are going to take s sub n and then r times s of n, and we're going to subtract it, and I'm going to show you guys exactly why right here. If we take s of n, we have a sub 1 times r all the way to a sub 1 times r to the power of n minus 1. When we do this next part, r times s of n, this is what's kind of interesting. What you guys are going to start to see is this entire portion from here to here, this entire thing is actually going to be this entire portion right here. So all of these terms are actually going to be shared. So if we end up subtracting them, what's going to be left over is these two terms here. And what we're going to be able to do is solve for that very, very simply. So what we're going to do is just subtract these from one another, and we're going to be left with, once again, those two terms. And that's where that comes in right there. But here's the thing. We want to find just the sum. So if you're taking a look at this sum, we have s sub n and s sub n here. So what we're going to do is go ahead and take that, and we're going to factor that out to the front, and then we're going to have s sub n right here times 1 minus r. But we don't want s sub n times 1 minus r, so what we're going to end up doing is we're going to take and we're going to divide through by 1 minus r. Did I just put negative r, or negative 1? Sorry. 1 minus r. Okay, we're going to do the same thing over here, 1 minus r. When we do that, this cancels, and then we're going to get a sum formula that we're going to be able to use for any geometric sequence. So the thing is, when you have a Riemann sum and you're looking at it, you're able to determine your first term and your common ratio from it. You're going to be able to just plug directly in from your sum or into the sum formula, and you're going to be able to find whatever you're looking for. And I kind of just went through here and copied the same thing. One of the things to denote here is that your common ratio cannot be 1 when we're using this form. That would end up just adding the same thing over and over again. There is no real change. If your r is 1, you're multiplying by 1 then. So what we're going to do is we're going to go ahead and find the 18th terms, find the sum of the first 18 terms. So what we're doing is finding the sum from 1. So this is from 1 to 18. Okay. Now, if we wanted to do that, we'd have to keep multiplying by r, go back and add all 18, but I don't really want to go ahead and do that. So what's going to happen is we're going to follow the same form. So we're going to take s sub n equals a sub 1 times 1 minus r to the power of n all over 1 minus r. And if we plug directly into this, we're going to be able to find our way. So the first thing we need to do is our first term is 2. A sub 1 equals 2. Okay. Our common ratio, the way you find your common ratio is you take your second term and divide it by your first term. So negative 8 divided by 2 is negative 4. Okay. And then there's one last thing that we're missing here. We're missing our number of terms. So if we're going from 1 to 18, that's going to be 18 terms. Okay, so what we're going to do is go ahead and plug directly into this, and we're going to have s sub 18 is going to be a sub 1, which is going to be 2, so we're going to have 2 here, times 1 minus r is negative 4, and you put that in parentheses since we're substituting, and n is 18. Okay, and this is all going to be over 1 minus -4. Okay, and when we do this, what's going to happen is we're going to plug this directly into our calculator. One of the things you guys are going to be able to do is just go ahead and plug this directly into Desmos how it is, but what I'm going to do is go through and clean it up a little bit. If you have minus and negative, it's going to give you a plus, so we're going to have 2, and then we're going to have 1 minus -4 to the power of 18 all over 5. Okay. What's going to happen, we're going to go ahead and plug this in. 2 times, open parentheses, 1 minus, open parentheses, -4 to the power of 18, close parentheses, to the power of 18, close parentheses, divided by 5, divided by 5. And what's going to happen in this case is we're going to get a humongous number. Let me go ahead and make sure I got this right. This sum, if we were to add the first 18 terms, is going to give us -27,487,790,694. I can't write that right there because it has a page term, 694. So as you can see, this is not something that we want to be adding and writing out 18 terms for. So this formula is actually going to be very helpful to us. Specifically when you guys start getting to your third portion of calculus, it's going to be very, very important. In your first couple parts it is too, but in that third part, it's all going to be about these sums. So this is going to be a very good base for all my kids who are taking BC or going into any of those fields that require high levels of math. Even the first couple levels, you guys are going to be seeing things like this. So what I'd like you guys to do, please go ahead and do the same thing and apply that to checkpoint 4 for me. So go ahead and take a moment for that. All right. So what we're going to be doing now is we're going to be using our Riemann sum here, and we're going to go ahead and we are going to do the same exact thing. But now we have to do, and we have to identify all of our pieces. So we know that this is going to be equal to, we're going to have to plug directly into it. We're going to have a sub 1 times 1 minus r to the power of n all over 1 minus r. Okay, it's the exact same form that we have from right up above. So what we're going to do is we're going to have to determine what all these pieces are. So the first thing is, our first term is going to be 6, and this comes from when we were writing out all of our terms at the very beginning. When we're writing out our specific notation, we even did it for example 3 here. A sub 1 times r to the power of n minus 1. And that's the same sort of thing here. So when we do that, we're going to have 6. This is our first term, is 6. Okay. Our ratio is going to be whatever we have as our exponential, so it's going to be 2. That's where we're going to get this part right here. This is going to give us our ratio, 2. And then our number of terms, n, is going to be from 1 to 10, so that's 10 terms. Okay. So what we're going to do is go ahead and plug directly into that. So we're going to have 6 times 1 minus 2 to the power of 10, all over 1 minus 2. Okay. So what we're going to do is go ahead and do the same sort of thing. We're going to have 6 times 1 minus 2 to the power of 10. This one's a little easier for me to do. 2 to the power of 10 is going to be 1,024 divided by -1. Okay, so when we do this, we're going to have 6 times negative 1023 divided by -1. I put a division sign in this instead of a multiplication sign. This is going to give us 6,138, if I'm not mistaken. Yep, that's what it is. It's going to be positive because we're going to have a negative. This is going to overpower it, divided by a negative, so that should give us a positive. So this is going to give us our sum from 1 to 10. Okay. What I'd like you guys to do is please go ahead and do checkpoint 5 for me. I'm going to go ahead and give you guys a moment for that. All right, and then on to our last part is we're now going to talk about an infinite sum. This infinite sum, this idea, is actually going to play quite a big portion in calculus. This is one of the big topics from this section. We're going to be seeing that actually coming up in our next few lessons as well. So far we found a sum from 1 to 10, 1 to 18, 1 to 32, and things like that. We're now going to ask what would happen if this sum went on forever. Now, the basic idea is if I keep doing it and it's by a whole number, and we keep multiplying by a whole number and adding it. So for example, if I had 2 times 2 to the power of 2, that number, of course, is going to go to infinity if I keep adding it. So the idea is when I have an R that's smaller, I'm going to be able to actually find these values. So let's go ahead and just talk about it for a moment. So an infinite sum is of the form a sub 1 times a sub 1 to the power times r, a sub 1 times r to the power of 2, and so on, and it keeps going all the way to n. With the first term a sub 1 and the common ratio r is called the infinite geometric series. How can we determine which infinite geometric series have sums and which do not? We can look at what happens to r to the power of n as n gets larger in this formula. Okay, so here's the basic idea. When you're taking a look at this, if r is any number between -1 and 1, the term r to the power of n approaches 0 as n gets larger. Okay. For example, consider what happens to r to the power of n, where r is 1/2. So if we have a ratio that is smaller than 1 or greater than -1, it's going to be a fraction. And when we're looking at it, 1/2 to the power of 1 is 1/2, to the power of 2 is 1/4, to the power of 3 is 1/8, to the power of 4 is 1/16, and this number keeps getting smaller. So if I take 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and so on and so forth, those numbers are getting very small as we're going. And so with these kind of problems, if we have an r value that's going to be less than 1 and greater than -1, then we're actually going to be able to find our sum. Okay, so with this, what's going to happen is if r is between -1 and 1, or equivalently the absolute value of r is less than 1, then we're going to be able to find the sum denoted by this. Okay, so we're going to be able to find the sum denoted by this. So what we're going to do is we're going to go ahead and plug directly into this in our first example, and I'm going to let you guys go ahead and do checkpoint 8 afterwards. So if it is greater than 1, there is no sum. Okay, it's going to go off towards infinity, and once again, that's a non-real number. So with it, the first thing we need to know is when we're finding this infinite sum, we need our first term and our ratio as it goes. Okay, so our first term is pretty kind of straightforward to find. This is going to be a sub 1. Okay. Our ratio, however, we have to take a look at it, and we can go through and we can do division. We can think about what we're multiplying by each time. So in this case, 3/8, 3/16, and we change signs. So we know our ratio is going to be negative because it's changing signs here and here and here. So the 8, what did we multiply it by? We multiplied it by 1/2. So it's -1/2 in this case. So when we're taking a look at this, let's see if it goes the same for the next one. If I multiply by -1/2, it changes signs again. 2 times 16 is 32. So it actually works out just fine. So what we need to do is just plug directly into it. We're going to find out what this sum is as we take 3/8, multiply it by -1/2, and add it all the way out towards infinity, where everything gets minutely small. So with this, we're going to have 3/8 over 1 minus 1/2, -1/2. These signs are very important when we're taking a look at these. So we're going to have 3/8 over 1 plus 1/2. Okay. Now I can always rewrite this as 2 over 2. That's the same as 1. And what will happen is I get 3/8 over 3/2. Okay. And at this point, we're able to take a look at that and know that we have two fractions. So we're going to be able to multiply by the reciprocal. And we're going to get 2 over 3. What happens with our 3's? Well, they cancel, and we're left with 2/8 or 1/4. So what does this mean? This sum, as it goes out towards infinity, and we add each of the parts of this series, or of this sequence, we're going to be able to go ahead and we're going to find that we get 1/4. Okay. What's going to happen, guys, is I want you guys to go ahead and check out checkpoint 8, and when you guys are done with it, your My Math Lab is already posted, and you guys are going to be working on that today. Have